velocity of the lower crust, which ranges from about 6.5 to 7 kilometers per second heat wave velocity, is consistent with mafic cumulants, with gabbros. It's not consistent with basalt. Also, when you go to ophiolites, where we have exposed sections of this kind of stuff, what you find in the lower crust is dominantly gabbro, with a few intrusions of trapped melt, but certainly not dominated by sills of melt. Okay? And so, to me, an acceptable model of the construction of the oceanic crust should satisfy the constraints that the mass of the primary melt coming out of the mantle can be divided into the mass that crystallizes to make the lower crust and the mass that erupts to make the upper crust. And likewise, the composition of every component of that primary melt that comes out of the mantle should be divided in a complementary way to the composition of the erupted section and the composition of the lower crust. Okay. So how does it work? Well, here's the Meltz fractionation model, starting from the primary melt of the Meltz model with potential temperature consistent with Christie et al.'s oxidation state. And here's the primary melt from the Meltz model consistent with the oxidation state from Cottrell and Kelly. And as we fractionate them and look at the mass of residual liquid, when we get down to a little less than about 8% MgO, which is the average composition of erupted glasses, what we find is that in the hotter model, we've fractionated by about 50%, and we could make a crust that's something like half liquid and half gaseous. Whereas in the colder model, we've only fractionated about 1/3 of the liquid mass, and we should expect an oceanic crust with 2/3 volcanic sequence and 1/3 plutonic sequence, which is not what we see. All right, one more problem, big problem, okay, which is if you go out and you actually look at mid-ocean ridge rocks, you have glasses and you have olivines carried by those glasses. And we think we know what equilibrium between those glasses and those olivines look like. Okay? And if you change your estimate of the ferrous iron in the liquid, that changes which olivine they are in equilibrium with. So if you go to a location and you find in a glass an olivine that is more magnesium rich than what should have been the first olivine to crystallize on the liquidus, then you have a problem. Then you have to say that that olivine is a xenocryst, that it came from somewhere else, that it didn't crystallize from the rock that it's in, or anything parental to the rock that it's in. On the other hand, if you find an olivine that's less magnesium rich than the liquidus olivine, that's fine, because this thing progressively fractionally crystallized from the liquidus on down. So here's an example of a very carefully analyzed rock, same one we looked at before, from the Siqueiros transform fault. The blue line is the primelt-free solution for the composition of the liquidus olivine as we change our estimate of the ferrous iron over total weight. Okay. And at 0.84, your prediction is that the first olivine to crystallize from this lava should have been about Forsterite 90.2, whereas over here at Christie et al.'s number, it's more like 90.55. And here is an olivine phenocryst from that same glass, analyzed from core to rim. The core is Forsterite 90.4. So the core here would be in equilibrium as the liquidus olivine at an iron 2+ over total iron of 0.88, Mesos and Humboldt iron. It's admissible for you to have started crystallizing olivines up here and this olivine to have started glowing later. It's not really admissible for the first olivine to be down here. Where did you get this olivine from in that case? It has to be a xenocryst of some kind. And if all of the olivines are xenocrysts, then you start to wonder what's going on. Okay. Likewise, from the same area of the mid-ocean ridge, we have lots of olivine-hosted melt inclusions. And we can take each of those melt inclusions, and we can run it through the prime melt-free model, and we can say what would be the first olivine to crystallize from the ancestor of that melt inclusion composition. And we can compare that to the olivine that actually hosts the melt inclusion. That's what I've done here. And the green symbols show what happens at ferrous iron over total iron at 0.92, the blue symbols are 0.88, and the purple circles are 0.84. Anything above the line is okay. Anything above the line corresponds to a melt inclusion found in an olivine that is more evolved than the first olivine that should have crystallized from parent technology. Is that a good sentence? Anything down here is forbidden. anything down here corresponds to a melt inclusion, okay, which should have, is hosted in olivine that is more primitive than the most primitive olivine that ever should have crystallized from the parent melt inclusion. And you see as we go from green to blue to purple, a lot more of the data come down into the forbidden region. Another way to look at the same information is from the observed melt inclusion composition, okay, how much olivine do you have to fractionate to get it into equilibrium with its host? And a positive number is okay, and a negative number is not. And so at a ferrous iron over total iron of 0.92, nearly all of these are in the okay region, right? Where something on the order of 0 to 10% olivine crystallized before the melt inclusion was captured. And at a ferrous iron over total iron content of 0.84, all the data are down here, where a negative amount of olivine has to have crystallized before the melt inclusion was captured, which is not good. Okay, so this is the crisis. The crisis is if the latest and greatest analytical technique is right, then everything I think I know about the origin of the oceanic crust is wrong. Okay? So what's the resolution? What's the way out of this dilemma? Well, one possibility is that what I asserted at the beginning, that the true KB is a systematic behavior, might be wrong. Maybe the apparent KB formulated in terms of total iron is actually somehow more systematic. This is in principle possible because the liquid is non-ideal. It's a complicated solution. And it's possible that as you add ferric iron to the liquid, it actually raises rather than lowers the activity of FeO. But I tested this in the MELTS model, and it's not true. Another possibility is that the oceanic lower crust is not actually complementary to the upper crust. And one way you could get that to happen is if a lot of the lower crust were made of trapped sills of liquid. Okay. Then you could have more lower crust for the amount of upper crust that you have. The problem is the more liquid that you start trapping down here in sills, the slower the lower crust is going to get sizable. Okay. And you're going to pretty quickly run into a situation, I think, where you cannot match the properties of the lower crust. Another possibility is that my method of inferring the primary liquid composition is wrong because the liquids coming out of the mantle have to come through the mantle lithosphere, which is relatively cold. And as they are doing so, they might crystallize olivine. But since they're still in contact with mantle, their magnesium number might stay buffered to a high value. And so you lose mass and you lose temperature, which the magnesium number doesn't start evolving down to more lower values. I don't think this works because I think it actually makes it worse because all of the mass that you crystallize and leave behind in the mantle doesn't end up contributing to the crustal phase. So it really makes it difficult to get the thick crust. And so either some part of the whole conceptual framework that I've given you of we think we know the composition of the mantle source, we think we know how it melts when it is drawn close to the surface under a mid-ocean ridge, and you extract the melts, and you bring them up into the crust, and you partially fractionate it, and then you erupt some. Something about that whole model could be completely wrong. Okay? Or the quantitative model that I'm using to connect what I think I know about melting of peridotite to what I think I know comes out the top, that could be wrong, and that's possible. Okay? Or maybe the answer is actually in the analytical arguments that I tried not to get into. Okay? I don't actually know. What I'm trying to do here is just tell you there's a problem that nobody else is talking about. Now you all know there's a problem, and maybe one day we will solve it. Thank you.
I don't know how you feel. It's a marathon for me. Out of breath. So questions out from students first. I've seen the comments from the faculty member. Any graduate students or undergraduate students, postdocs, who are able to, yes.
And so the oxygen to gas is measured. Actually, the ferrous iron ratio measured in the basalt. There are fresh glassy marks inside the from the mid-ocean ridge. Is it possible that while eruption they reacted with the water, and that caused a little bit change in the oxygen viscosity?
It is possible. So you can to some extent monitor the amount of contamination of the salt by seawater by looking at the chlorine. Contamination by seawater dries up the chlorine super fast, so you have some idea of how much seawater has been assimilated. And the fact is, assimilating seawater doesn't actually oxidize you very quickly because bottom waters don't have any oxygen in them in most places. But the abyssal periddotites that we think are residual, you can analyze the solid oxide mineralogy in them, and you get an FO2 of about QFM minus 1.5. Okay? And so if you want Cottrell-Impelli number to be right, you have to go up by about 2 orders of magnitude by this alteration or some other alteration process. The other strange thing is that it would have to be systematic. It would have to affect all mid-ocean ridge basalt classes more or less equally because the distribution is very tight. Pretty much everywhere you go, depending on which analytical technique, you get the same number everywhere you go. So if you want to blame it on seawater alteration, you have to make it very systematic. But for example, the chlorine contents are all over. Yeah, it's worth checking, but I don't think it solves the whole problem.
We take another student question.
So what is the relation between time and the atmospheric content of basalt? Or there is no relation at all?
Between
Age.
age.
Another question is, where do you think those atmospheric gas coming from? Is that from the atmosphere or from the oxygen pump?
That's a very hard question. Zero-age mid-ocean ridge basalt classes are easy to find and easy to analyze. Old mid-ocean ridge basalt classes are hard to find. They don't last very long. They devitrify within 100 million years under optimal conditions, and they're covered by sediment. And we don't know that much. We can't really extend this reasoning very far back into the past. And so discussions about how the redox state of the mantle has changed over time and whether you can see the signature since the end of the Archaea and its subduction of oxidized material is something people still argue about. And it's an argument that's rich in speculation and poor in data.
Me? I'm a paleomagnetist, and so when I look at Moore, I see an enormous variety in the matter to me, which is the titanium magnetite. And I see variations in grain sizes from nanoscale to nanometer scale. I see titanium content varying. I see lots of other things all varying. And notably, the oxidation process to medeimite. And I can't imagine that with all those variations and heterogeneity, that you can't find a few other things to blame.
So all of that happens later in the evolution and crystallization process than the part that I'm focusing on. So if you look at the liquid line of descent of mid-ocean ridge basalts, you saturate with an oxide phase, usually magnetite, sometimes ilmenite, down around 4% MgO. And so when we have glass brines that are quenched at 8% MgO, they haven't got any oxide in them. And if we trace them back to the primary melt, oxide was not involved in the fractionation process at all. If you go down the other way towards the whole rock and towards more evolved compositions, I totally agree that the petrology and the mineralogy of the oxides are complicated and that the redox state of the rock does evolve. And, we've known that there's 1 or 2 log units difference between the glasses and the whole rocks for a long time. So hopefully, as long as you stick to reasonably primitive glass samples that are not yet saturated in oxide, that's not going to be a big source of confusion. There is often a spinel phase close to the liquidus, but it's chrome spinel, very low ferrocyanide content.
Could the problem be that all the crystal or low ferrous ratio that data set were built into all of the models they are using? For example, the MELT model. Also built into how we infer the mantle composition. Because that's a 1986 paper, very old and quite accepted everywhere it's implemented.
It is certainly worth sitting down carefully and tracing all of the logic chains all the way back through the whole entropy